Alright, so we're going to pick up where we left off with radical expressions the other day. When we were simplifying radicals, we said if I want the square root of 16, then I'm going to find the number that when I square it, I get 16. Or if I wanted the cube root of 125, I want to find the number that when I take times itself 3 times, or when I cube it, I get 125. And everything that we simplified in the last section cleaned up nice and neat. And we had an integer value for that. Maybe I had a negative number, and we said it's okay to take a negative or a root of a negative number as long as that root is an odd root. So the fifth root of negative 32 is negative 2. But if I stuck a negative sign in front of either of these 16s, I would stop and say that, well, those aren't real numbers. Today what we're going to work with are things like the square root of 20, or maybe the cube root of 250, or the fourth root of 80. And if you break those numbers down, the 20 or the 250 or the 80, the square root of 20 is not an integer value like we had over here. If you type it in your calculator, you're going to get some decimal between 4 and 5. Okay, but just because it's not an integer value, that doesn't mean we can't go farther and simplify it more. So what we're going to work with today, what we're going to look at is there's a rule, and there's some restrictions on this rule. But I'm not going to point them out and spend a lot of time focusing on them until we get a little further down the road, and then we need to go back and pay attention to those if-thens. But really, if this is a well-defined number, if it's in the domain of what we're doing, then if I want to take the nth root of a product, I have two or more things, I can take the product of their nth roots. Meaning if I want to find the square root of 4 times 25, I can take the square root of 4 and multiply it times the square root of 25. The square root of 4 is 2, and the square root of 25 is 5, and 2 times 5 is 10. Now, a radical is not considered simplified completely unless every factor that can come out from under the radical has been brought out. So let's go to another page and kind of talk about what I mean by that. Alright, we just walked away from the square root of 16. I don't want to use that number. Pick some different. Square root of 9. And if we count on our fingers, if we think about our multiplication tables, we can figure out pretty quickly, hopefully, that the square root of 9 is 3, because 3 squared is 9. And we said we had cube root of 125 on the last page, and we said, well, 125 is 5 cubed, and so the cube root of 5 cubed is equal to 5. Or maybe I have the fourth root of something small, 81. And then if we recognize that 81 is 3 to the 4th power, we say, well, the fourth root of 3 to the 4th is just equal to 3. If we write it this way, and I'm not saying that you have to write it this way if the number is nice and neat like this from 7.1. But with the problems that we're going to be working with in this section, our goal is to create a situation where those roots and those exponents match each other. If I have a square root of something squared, or the cube root of something cubed, or the fourth root of something to the 4th, then all that's left is that something, that factor there. Meaning if I ask you to tell me the 5th root of x to the 5th, or the 6th root of p to the 6th, or the 11th root of 5 to the 11th power, maybe the 8th root of 11 to the 8th. And in each of these cases, since the root and the exponent match, I know that factor gets set free. The x or the p or the 5 or the 11. So we'll say this is equal to x, it's equal to p, it's equal to 5, it's equal to 11. Okay, almost. I'm going to come back to this one here in just a minute. So our goal when we're simplifying radicals is to find as many of these as we have available to us. And if the root and the exponent match, then that factor gets to come out from under. Now back up here to the square root of 9, when we said, well, the square root of 9 is 3 because 3 squared is 9. Recognize that there's another number that I can square and also get 9. If I square negative 3, I get 9. However, when we see this radical symbol on our paper, okay, if I have two possibilities like this, 3 and negative 3 both squared are equal to 9, we're still only going to write the positive number here, and we're not going to care about that situation. Okay, this symbol, by definition, by convention, means the positive or the principal square root of that number. Okay, same thing down here with this 3. If I take negative 3 to the 4th power, I also get 81. But this radical symbol here, 4th root of 81, when it's written on your paper, it means give the answer positive 3 and only the answer positive 3. Now notice on this middle one that I skipped over that there is no ambiguity here. If I cube negative 5 instead of positive 5, I get negative 125. Which means there is no positive case, there is no negative case here. This is the only case. The only cube root of 125 is positive 5. If I asked you for the cube root of negative 125, then I would say, well, that's equal to negative 5. So if you think for a minute, you think, well, when does this happen? When do I have to worry about it and when do I not? And we're back to what we talked about last section, and that's even and odd. If I have an even root, like a 2nd root, a 4th root, a 6th root, an 8th root, okay, then I always need to make sure that I only give a positive answer there when I simplify things. If my root is an odd number, like 3 or 5 or 11, then if the number underneath is positive to begin with, my answer is positive. And if the answer, or if the number underneath is negative, then my answer is negative. So stepping down here again for a minute and looking at these things here, I said, well, if I have the 6th root of p to the 6th, okay, I need to be sure, since that is an even number, that I give a positive answer for that. And if I've not told you anything about p, I can't guarantee that I just wrote a positive number on my paper, because maybe p is equal to negative 12, or p is equal to negative 1/2. So in order to cover our rears, make sure that we don't break any rules, I need to make sure that I give a positive answer, which means I need to have absolute values around that p. Now what I'm not going to do is come back up here and put absolute values around this 3 or that 3 or this 11 right here. Okay? Because when I write 3 or 11 on my paper, it's understood that I mean positive 3 and positive 11. But when I write a variable down, when a variable comes back out from under the radical, and when it was an even root to begin with, I need to put absolute values around it to ensure that the answer I gave was positive. Now, please understand that I'm not going to put absolute values around that one. Okay, my x here, because it's an odd root, maybe x is a positive number, but maybe x is a negative number. It all depends, and both are allowed. Okay. And if I put absolute values here around that x, I'd actually be wrong, because there's a chance that that answer is negative, that 5th root is a negative value. So the only time you have to worry about absolute values are when you pull a p or a q or an a or a b, a variable, out from under an even root. Wrap it in absolute values to make sure it's positive. We'll come back to these examples, if it'll turn, and more details in the next video.